All right, I guess let's kick it off. So I'm delighted to host Raffi, who met many of us at UPSLA back in the fall. He is not far away. He's just across the river at Hunter College in the Graduate Center in Manhattan. He works in the area of software engineering and programming languages and systems, and some stuff that pertains to AI and machine learning, which you might talk a bit about today. Earlier, Raffi was a software engineer at Apple, and he did his PhD at Ohio State. And this is a great homecoming for him because he's actually from Madison, New Jersey. So welcome back.
Thank you. I appreciate it. Yeah, thank you for having me here today, and thank you for giving me a talk. So today I'd like to talk about challenges in migrating imperative deep learning programs to graph execution, which is an empirical study that we recently did with my colleagues. Tatiana is my PhD student over at the CUNY Graduate Center. Vinny Bengarzadeh is my colleague at Oakland University, and Anita Raja is my colleague at the CUNY Hunter College. And this is work that we're actually going to present pretty soon here at MSR 2022, Mining Software Repositories, which is co-located at ICSE 22 in Pittsburgh. So hopefully that's going to go. I think that's a hybrid one as well. So we'll see how that turns out. It's kind of strange as they split the sessions up. There's like hybrid before and in person afterward, but we'll see how it goes. So deep learning systems and runtime performance is sort of the main theme surrounding this work. And even though it's AI related, I'm going to be talking about the programming of AI programs in particular. So deep learning systems, along with the broader class of machine learning systems, are pretty pervasive in today's society. And deep learning particularly deals with a lot of data. So its data set is going to be very large in order for it to be effective. And when we're talking especially about industrial deep learning systems that may do like online learning or have some kind of user interaction with either classifications or predictions, responsiveness of these systems will be very important. And traditionally, the way you develop a deep learning program, you would use a deep learning framework, kind of like TensorFlow or PyTorch or some other ones, MXNet. And traditionally, they've been using this deferred execution style API or programming style or paradigm, where you build the computation ahead of time and then you execute it at a later time. And that allows the deep learning framework to run your code very efficiently because it knows what's going to happen ahead of time, and it can plan the execution of that and all sorts of great stuff. And then it's basically graph-based computation. So that's great for efficiency. However, for development purposes, it's not so great. There have been many studies confirming that it's basically error-prone kind of paradigm. It's very cumbersome to code in this paradigm. And it produces programs that are difficult to debug because of the deferred execution style. I'll show you an example of that in a moment. And basically, because the graph computations execute statements in a non-imperative order, another problem that you have is that traditional tools that you typically use with programs, like debuggers, for example, are kind of inapplicable for this kind of paradigm. So they kind of necessitate their own tool and support. So here is an example, deferred execution style deep learning code snippet. This one's in TensorFlow. So lines 2 to 4 here, we're going to build a computation graph. So it's A and B are tensors, and so is C. And C is the result of A times B. Then we're going to launch what's called a session in TensorFlow. This is basically the older version of TensorFlow that supports deferred execution. And then we evaluate the tensor C by running the tensor through the session. So we build the computation first. Then line 4, which is the this computation here, does not execute actually until the session that's created on line 7 runs on line 10. Right. So we don't get actually the execution until here later on. Some other problems with this paradigm is that there is no native support for like common iterative, imperative rather, programming constructs, or for example, like iteration. You need to use like these very cumbersome APIs, for example, in TensorFlow, which is not so fun. Okay, so people realize this is not such a great thing. So can we do this more on an eager basis? So, and can we do it more on an imperative basis as well? So imperative deep learning programming emerged relatively recently. And it allows you to write DL programs in a way that's more natural, less error prone. You can use existing debugging tools on your imperative deep learning programs. So some of these frameworks are TensorFlow Eager, which actually was now incorporated into TensorFlow 2, like the latest version of TensorFlow. Keras, which is also incorporated into TensorFlow. PyTorch is the one from Facebook, which kind of initially started out as an imperative deep learning framework. And all these frameworks, they encourage eager execution. That's how their APIs are designed. That's how you code and use in these kinds of frameworks. However, you don't get the benefits of the deferred execution style code. So you unfortunately sacrifice runtime performance. And when I talk about performance in this talk, it's going to be runtime performance. I know like performance is another kind of overload term for AI in particular. So yes, we're talking about runtime performance. So yeah, you sacrifice that. So naturally hybrid approaches emerge to try to get the best of both worlds and bridge the gaps. And these approaches, there's several of them. Like each kind of framework has its own approach. Hybridize is the one that's from MXNet, which is an Apache project. Torch script is from PyTorch, which is like a JIT for PyTorch to run imperative programs. And Autograph is the one that has been integrated into TensorFlow. So they all kind of came out separately, but they eventually got, maybe not Torch script, but especially Autograph actually got incorporated into the mainstream distribution of TensorFlow, which is now TensorFlow version 2. So what these approaches do is that they allow you to execute into your imperative deep learning programs as static graphs at runtime. So basically you get the best of both worlds. So here's an example of imperative deep learning code. This is like pretty modest model for image classification. It's actually using the Keras framework, and as you can see, that's now integrated into TensorFlow, which is why I have a module name there. And what you do in TensorFlow 2, in particular here, when you write imperative deep learning code, is that you write, this is actually object-oriented, which you could also write previously, but what the new thing is here that you decorate your functions with what's called TF function API. So you can either decorate your function using this, or you can call it as a function, which returns another function that's now like hybridized, is the way it's called. The more common way is to do it this way. And they can take any optional arguments that you can add there. You can just customize how that works. So on line 10, what happens is that Autograph is actually going to be invoked here to enhance possibly the performance of this code. So yeah, one way you can do that is decorating the call method of a model, which will do the learning, and subsequently the prediction, class, in this case actually it's classification. Another thing too is that you optionally provide, as I mentioned, arguments in TF function. I'll talk about more of that later. You can control how the migration works, and it turns out that those are quite influential. So what happens here is that at runtime, when the call method gets executed, the runtime will trace that method and build a static graph. And it will use that graph in subsequent calls to the method. We tried this out just on our own little like Google Colab or our Jupyter Notebook, and we ran it a few times. And average, actually, it's a 9.2 with using and without using TF function. So, and this is like just a modestly sized image classification model. So yeah, so the performance gains could be significant. Okay, so like the other two approaches we talked about, there's actually drawbacks of hybridization, unfortunately. So they do necessitate non-trivial amounts of specialized metadata. So for example, you have to annotate, right, your imperative DL programs with TF function on certain functions that you want hybridized. You also may have to provide parameters to TF function. There's also like a bunch of known issues with TF function and limitations of where and when you can't use it, and also where it's applicable, where it's not applicable, where you might actually have to change the code of your function before applying it. So, several considerations are required to make the code that's going to be hybridized. That's the function that has a TF function decorator on it, for example. Enable the safe, accurate, and efficient graph execution, because it actually turns out you can make your performance worse using TF function, which is crazy to think about because that's the whole reason you would use it. And the several considerations are also required to avoid performance bottlenecks, as I mentioned, and perhaps even worse, semantically equivalent results.
Yeah, a quick question.
Yeah, sure.
Can you give me a sense of what the rules are for when you would annotate and when you wouldn't?
Great question. We're going to talk about it a little bit, but it's transitive. So if you annotate one function and that function calls another function, that one also becomes a TF function.
Okay, so the whole downward closure has to all be ready to go.
Right. Yeah, and it's not so clear of where you should add it, but a common place is to do it in a model call function or something that's responsible for like learning the training function of your model. So something that's going to take a long time. That's another thing you have to kind of understand is, what's going to take a long time, what's not going to. Because there's also overhead associated.
So you have to like first do some profiling to figure out where.
You may have to do some profiling, yeah, or just have a good feel of when and how to use it. So, but that's certainly some future work we're looking into is how to automate that process of where and when not to use it, so that it be available to people that are not like seasoned experts in systems. And it's typically like a lot of data scientists may not know, like, okay, this is when I should use it or not use it. For example. So, yeah, great question. All right, so let's take a look at TensorFlow code that produces side effects when applied to TF function. So how that works. So side effects producing native Python statements, for example, printing, appending to a list, or mutating global variables are actually problematic for TF functions. And I'll say from now on that TF function is like a TF function decorated function or a converted function or hybridized function. And the reason is that because they're traced at runtime, basically the function's behavior gets etched into this graph, right, that gets built. And this can result in something, in your results being unexpected, right? Basically, the side effects get executed multiple times or not at all.
Can I get a,
Sure.
Just to clarify, lines 4, 5, and 6 should be outdented, or is F some crazy non-terminating recursive function?
They should be outdented. Yeah, thank you for that.
Thank you.
Yeah, sure.
I was getting worried.
Yeah, sorry about that. That should be here. Sorry.
Okay, great.
Yeah, gotta love Python. Right. Sorry. That's another thing we talk about, that you actually can't use recursion.
Sure.
So yeah, so what happens is side effects occur when TF functions are called for the first time, but any subsequent calls with similar arguments, and that's a little bit of an overloaded term, because we're going to see how that can vary, execute the graph instead. So what happens here is that, yeah, thank you for that. These should be outside. So actually, this code would print, instead of 1, 1, 2, it would just print 1 and 2. So the first one works fine. It's really the second one here on line 5 that's a problem. Okay, suppose you want to safeguard some variable access. Perhaps you're trying to save on performance by not executing the same thing twice. So here we have some imperative TensorFlow code that uses a counter to do that. So for example, a model may use a counter to safeguard, as I mentioned, variable declaration. So the initial value of counter which is on line 4, right? Initially 0, is captured during tracing upon the first model execution, which actually is line 14. However, the variable v is incremented unconditionally at line 10. So even though this is an if statement, and this indentation is correct this time, line 10 actually is not included in the part of that card. And this happens because in a lot of cases where you're migrating to graph execution, you may not catch all these sorts of things, and it's actually going to result in suspicious numerical results. You can actually have lower performance from using TF function because perhaps you're safeguarding some kind of performance savvy statement, right? That you're trying to not execute multiple times. So in this case, you're actually expecting 1, 1, 1, but because line 10 is actually being executed unconditionally, you get 1, 2, 3. So developers are basically burdened to use TF function and other hybridization technologies.
I'm sorry.
Sure, good.
Can you go back one slide again?
Yeah.
I'm sorry, I just want to double check something. So the models are all sharing a self?
This is part of the model code.
Yeah. Oh, and so it's capturing self.v.
Yeah.
And it says, well, there's only, I mean, but what's crazy is look, it's 3 different models in the code on lines 12 through 14. Oh, no, it's
No,
one.
it's
Oh,
one
I'm
model.
sorry.
Yeah, it's the model on line 12.
Before you were creating 3 different models, now it's the same model. Okay, great. Great.
Yeah, it's the same model, and then you're calling M 3 times.
Got it. Okay,
On line 14.
that makes more sense. Okay, sorry.
Yeah, no worries. Yeah, stop anything. Yeah, so there's a lot of burden on developers here to write correct and efficient code in their deep learning software. So let's say they have a system that they use eager execution on, right? They're writing imperative deep learning code, and now they want to speed it up, right? Using hybridization. However, developers are burdened with making their code compatible with the underlying execution model, not the deep learning model. And also, as Eric mentioned, right, manually specifying which functions should be converted and actually how they should be converted. So, for example, how often should a TF function be applied? Another thing is calling TF functions recursively actually could result in infinite loops. And even if they seem to work, actually the TF function could be traced multiple times, which actually would result in what's called retracing, which is another thing that lowers your performance. So you have this situation where the graph keeps on getting built and built and built over and over again for the same or similar kinds of arguments. And you actually would have better performance had you removed TF function, believe it or not. Another thing I mentioned before with Eric was that there could be some overhead associated with converting or hybridizing your model code, and which could be very bad for small computations. So that overhead could dominate the time you would save by hybridizing. All right, so here's an example of using hybridization parameters. So in this listing, we have some DL model client code, not the model itself, which uses different data sets. So the model, right, is declared on line 1, and then we call the model, right, with different varying data sets. These are this very small example. So one data set, right, has cardinality 3, the other one is 5. And we get the following warning when we execute the code. 5 out of the last 5 calls triggered TF function retracing, is what I explained in the previous slide. And then actually it says tracing is expensive, but tracing is, if you recall, is this process of building the graph at runtime. So in this situation, you decorate actually the correct function, which is the model call function, but you use, or the person that wrote is, use the incorrect decorator arguments, or basically configure the hybridization process incorrectly, and it results in retracing, which actually gets you worse performance.
Why does it retrace? Like, I mean, Tensorflow knows that it's already built the graph, but is it that when it just gets, like what is it that's, why can't it just reuse the graph?
You have to give it some more information about the shape of the tensors, it turns out, which I'm going to get to also in a little bit. But yeah, it's this last bullet here. So invoking the model multiple times using different data sets produces the wording on the right. So in the cases that it can't abstract away the different parameters, it says, oh, can I reuse the same graph? So it's really about the shape. So what you can do here is actually you can give it like a shape wildcard, and you say, hey, build a graph that's general enough to handle shape X to Y or something like that. So yeah, great question. Yeah, so actually the way you do that is using what's called an input signature. And that's a parameter to the TF function decorator. It's also the parameter to the TF function call, if you want to do it that way in a functional way. So you add what's called a tensor spec, and the none here is actually it's a dimensional wildcard. And then the D type is also part of this problem. I'm not going to talk too much about it, but that's part of it's almost like a kind of like you're adding types to the tensors to give the runtime a little bit more information about how the static graph should be built. So yeah, so the none dimension and the tensor spec rather allows for flexibility of the graph, so it makes the graph like more general. That gets built, and since the tensors are matched in their shape, a none wildcard allows TF functions to reuse the traces instead of rebuilding or retracing. And it's going to occur when sequences or images are of different length or size, like we saw in the previous example. And since there's no call since each call no longer produces its own trace, the warning disappears, and now you're getting some good performance. So actually, you would add this to the previous example.
Can I ask a
Yeah,
follow-up? Why isn't this the default?
That's a great question. My guess would be that there's probably some overhead in doing something like this, or maybe they want developers to have quite a bit of control over how the graphs are being built. But I guess it also probably be that you would probably have less performance had you like let's say like in the previous example.
You're going to invoke it only once. Then
Or you invoke it on the same data set multiple times.
Right, and so then
or similar size data set, I should say.
Sorry, so then you could build a less general graph maybe.
Which may be more performant than an abstract one.
Got it.
Yeah. So it's not really the data that's the problem, it's the dimensions of the data. It's the input shape of the tensor. So,
right.
Yeah, so if we give it a data set with the same dimensions, then that would be probably fine. So once you start changing the dimensions, and then the dimension in like a deep learning could kind of be like a feature or something like that, or it could be like some just more characteristics of the data. So, but I'm going to talk about like in a minute here alternatives to hybridization. So yeah, so something might come in your mind now is like, well, if there's all these problems with hybridization, why bother, right? I don't know if that's the next slide or not, but yes, it is. Yeah. Great timing. Yeah, so exactly. So there are alternatives to hybridization. One is called Janus, and what Janus does is it does not necessitate that you annotate the functions with any kind of marker or give it any kind of configuration. So it just tries to figure out how to do the hybridization itself. So you just write the imperative, deep learning code, and no decorating, right? And then you run it through Janus, and then it tries to squeeze as much performance out as it can. However, it requires a custom Python interpreter, which may be impractical for industry applications, right? Where you have like these things running on virtual machines, but you can't easily change the interpreter. Or you're switching, maybe you're doing virtualization and you're switching Docker images around and stuff like that, who knows, right? Another thing is that only for specific Python constructs, so basically they have to engineer for every construct, like how the hybridization works. That can be very problematic, especially for Python. It's gone like a very large, it's undergone a very large change in the past few years, right, from Python 2 to 3. And Yeah, so update, yeah, so you can, every time there's a new language version, right, it has to be updated for consistency. And as I mentioned, yeah, so Python's gone over, like, historically underwent major revisions. So there's a number of downsides for that as well, which may not, it may be actually fine for, like proving a concept or something, or like in a biology lab where you run the experiment once and then you're done with it. But if you're an industry application, where your deep learning system is long-lived over a number of years, for example, right, it may not be so practical in an industrial setting. So that's really like the focus of this work, is really on the kind of industrial deep learning systems. So if you're actually, you don't really care, if you're in a setting where you're a lab that you don't really care about the performance of your deep learning model, because you can just come back overnight or something like that, it's you're probably not going to use hybridization anyway. So. All right, so the motivation for this work, for this study, is that there is a knowledge gap on how hybridization is used in real-world deep learning applications. We're typically interested in knowing what kind of challenges are involved in successfully applying hybridization in real-world systems, or at least open source systems, or at least just developers in general. Right? What are the kind of problems they face? How can things be improved? And we claim that without such insight, deep learning systems may be inefficient, fallible, and difficult to maintain. And we saw some examples of that. And really, like any kind of advances in deep learning that the frameworks come out with, right? So the frameworks are always like churning out new versions, especially Tensorflow. Like Google's always churning out new features and stuff. But if you can't use them correctly, right, then it's not really so helpful. So no matter how much you tune the runtime and the framework, if the API calls are not correct, then you're not going to get the benefits that you have from that advanced technology. So to fill this gap, we performed an empirical study on the common development challenges in migrating imperative deep learning code to graph execution, as we've seen in the previous examples, in smaller examples, but on a larger scale. And we took a look at how hybridization migration works in open source deep learning systems. And what we're looking for is bug patterns, challenges involved in writing reliable yet performant deep learning code. And we focused for this work on hybridization in TensorFlow. It's quite popular. They also have probably the hybridization TensorFlow is probably the most used. I feel like things like PyTorch are probably used more in that kind of the lab setting that I mentioned. And we found enough data for our study, so it seemed to be pretty good. But we feel that the concepts will probably generalize into the other technologies as well. They're quite similar in the way they work. They just work for other frameworks. So, like they have annotations too in the decorator stuff. So the hope is here that we can drive the automated approaches to migration. So like Eric was mentioning, right, we can maybe computationally approximate, which functions should get TF function, which should not, what arguments may they get? Are there any incompatibilities between the arguments? What code is amenable to hybridization? What code is not amenable to hybridization? Maybe some suggestions on how you can change a code to be amenable to hybridization through automated approaches. So that could be something like an embodiment of IDE code completions. There's also another angle here too, that there's, especially in this area of like mining software repositories, there's a lot of what we call MSR tools. So like tools that mine large open source repositories, and then particularly for refactorings, which are semantics preserving source-to-source code transformations, program transformations. So there's one in particular that deals with data science programs, and particularly Python, called Refactoring Miner 2.0. And so, yeah, so one thing we could do there is actually add this kind of identification into such tools, and to have future research.
So you mean identifying when people are refactoring to use hybridization? Yes,
exactly. Right, and different kinds of refactorings would be like, removing or adding or changing, the input shape, stuff like that. Exactly. So our goals are, to advance this kind of real-world knowledge of this emerging and pervasive hybrid paradigm. So the idea is like it's being used quite a bit, but we don't know like what adverse effects it will have. So this can provide feedback to the language and API designers for future versions. Could help tool designers comprehend difficulties, right, with writing performant imperative DL code, which you can integrate tools to do or to help with. What we also do in the paper is that I'm not going to get too much into it here, but that we put forth like some preliminary best practices, recommendations, and anti-patterns for practitioners using hybridization to use that technology effectively based on our study. And lastly, it could help educators assist in teaching hybridization. Maybe data scientists, right, that are learning, deep learning, and maybe incorporating hybridization into the course curriculum using like data-driven approach. So for the study, we looked at, as I mentioned, open source deep learning applications. We picked 250 of them. They're all Python projects because they have to be clients of Tensorflow using the Tensorflow version, Python version of Tensorflow. All these subjects together make up about 19.7 million lines of code. And this is not like a super large scale study because we manually analyzed the systems ourselves. And the way we picked what to analyze was assisted by tools, but the actual examination was manual. And I hope, as you can see from like the previous examples, like it's not so easy to find the problems right in this code. So it can be pretty hard to do it completely automated. And we want to get also a better feel of what the problems are in a more thorough fashion. So we look at Git commits and particularly GitHub. So these are going to be your code patches. We examined 470 of those. And we also examined 446 bug reports manifested as GitHub issues in these open source projects. The projects vary in domain, application size, and popularity. We actually got a pretty big spectrum of different kinds of deep learning systems. So we didn't want just like the software was developed by Google or Facebook or I guess Meta now. We also want to know well, what are students doing? What are chemists doing? So on and so forth. So we try to vary the data set quite a bit. So we did have like some that have like a lot of stars, forks, and collaborators on GitHub. We try to mix up the kinds of DL applications like libraries and frameworks. Actually, we actually analyze like TensorFlow itself in some of our studies. So they actually do use TF function in their own code, which is another question about how you. So another interesting question is like from like a software engineering standpoint is like, well, if your framework is using TF function and now you're calling an API in that framework, like you have to use TF function, or I know it's transitive, right? But there could be some adverse effects of how that works. So there's also some previous data sets where the projects were also used. We took some of those. We also verified there's some non-trivial part of the system had a deep learning component. So we said that was the deep learning system. So some of the projects are from like very big names like Apache, Apple, Google, NVIDIA. But like I mentioned, we also included some like that no one knows about because we wanted to see like even what are the struggles that even like less experienced people are having. Okay, so the study is really broken down into two parts here, right? Between the Git commits and the bug reports, which are GitHub issues in this case. So for the Git commits, we mined Git commit chain sets for those mentioning referring to TF function. Issues, we did more of a natural language approach, right? We searched for the actual text of TF function. And hybridization is relatively new. It came out like at the end of 2019. The TF function was released specifically in a TensorFlow case. So we didn't expect to see like a lot of stuff, but I think we had enough for our study to get some good insight. So for the chain sets, we use a tool called Git cprep. Actually, this is by Shaki Ray in Columbia, one of her team members. It stands for Git commit processing. And what it does, it classifies Git commits. So you can give it like a keyword. You say, hey, search for this API. It also uses an NLP to figure out whether or not that represents like a bug fix using the commit log. It's not 100% effective, but since we're manually analyzing the commits, we can decide right ourselves if it represents a bug fix, which is what we did. So this is really kind of narrowed down the search space. For the issues, we basically issued standard GitHub search API right on TF function, and we filtered. We ran actually some of the issues, all the issues rather, through a model to see like the discussions were like relevant. So there's some previous work also that deals with classifying issue comments, the discussion comments, and seeing whether or not they're like social conversation or they're solution conversation or workaround conversation. So we made sure that there was some kind of relevant conversation there.
You focused on trying to identify bugs that pertain to TF.
Yeah.
So that at least things that were discovered to have been bugs, but not necessarily uses of TF function that is not yet known to be buggy, even if it is.
So in the case of the change sets, that's completely true, right? Because it has to be a commit that fixes the bug. Yeah. So in the change set case, it's true that there could be bugs that we don't know about that are in the code that we completely gloss over.
Or uses of TF function that are correct. That was also not relevant. Like uses that were correct the first time and never had an issue.
Well, for the commit case, it has to have a bug fix. Commit.
Right. So
yeah.
What I mean is that instances of the use of TF function that was just like someone added it to some function, and then they never had any problem with it, that would not come up in the collection that you found?
Most likely it would not.
Okay.
Unless they said something in the message that kind of was deemed to be probably they're fixing a bug.
Okay.
Sometimes like what the git commits like would look like is that they say they're fixing a bug, but the commit doesn't only have one change in it, so there's like multiple changes, and they fix some bug elsewhere, but they add TF functions somewhere else. Yeah, I mean, right. And that was like perfectly fine. Yeah, that wasn't a bug. So yes, that's why the manual inspection is quite important. But yeah, in the issue case, right, these are like, for the most part, these are developers that are filing against Tensorflow, saying like, hey, this is not working for me, what do I do? And sometimes, they're using it wrong, sometimes they're using it correctly, but there's a bug in Tensorflow, and sometimes there's the third situation is like, there's a bug in Tensorflow, but there's a workaround, they're not gonna fix it because it's some other problem, and we're not gonna fix it anytime soon, so they give them a workaround. Sometimes they say just live with it. So, maybe 4 situations. All right, so here's just a quick overview of our subjects. And again, the study's broken down into two parts, right? The bug fixes and the change sets and the issues. And this is like how many we found just from our automated search. So the commits, and this first number here is the commits. This one is the issues, right? This is the total. And this is kind of broken down by the keywords. So as I mentioned, hybridization is relatively new, so we weren't expecting a whole lot of data, especially in the change set one. So we got 470 for the change set study. We just examined all those right straight away. We got more for the issues. And then from that was a little too much for us, so we had to select that down a bit. And I'll talk about how we did that. Yeah, so the manually examined code patches, right, 470 was manageable for us. So we just went ahead and did all of them. A lot of times, like to discover what the problem was, we reference bug reports. Sometimes that was the same bug report from the issues, but we excluded those from the issue data set. So that helps us like understand what the problem is. We can also look at the commit log messages to get an idea. Sometimes we actually talk to the developers directly, and actually both times. And what was really interesting about this study, like from a software engineering or HCI perspective, was that the developers that were like the newer developers that were from like lesser known projects actually responded more frequently than the ones from like more mature projects. So I was glad that we could use those because we got a lot of good insight. So yeah, so for the GitHub issues, we randomly selected a subset to manually examine, and what we did there is we actually favored ones that include some kind of code snippet where the developer would show, hey, this is the code that has a problem, so that way we can get more insight of what the usage scenarios are. So yes, we manually examined all these things to determine like the hybridization bugs or usage challenges that they were experiencing. As I mentioned, we contacted developers on occasion, and we formed a hierarchy in part by using a Tensorflow documentation. So this is kind of the like hierarchical depiction of our category. You can see here most of the problems were related to performance. I'll get into that a little bit in a bit, but definitely paper has more details. We also broke this down in a top level view. So that was kind of like a hierarchical view. This is just looking at the top level. Again, you can see performance is the most problematic area. And just some like highlights of the findings. So just a very quick overview of what we found is that hybridization is prone to API misuse, which means that developers are not using hybridization techniques according to the documentation. It also can result in performance degradation, which is the opposite of this intention. It's really pervasively used was another thing that we saw, even though we didn't get like too many hits in the git commit search, but it's used quite a bit. And it has limited application due to execution mode and compatibility. For example, like where some part of your code is executing eagerly, some other part of your code is executing like deferred execution right in the graph mode, and there's problems talking to each other. So specifically, again, we found that performance was the largest category involving TF function uses, so about 40% here. We found about 7% of cases where TF function actually caused performance issues, as we were talking about before, and had to be removed. Only about 54% of problems, 55% of problems compared to DL code performance were fixed by adding TF functions. So performance problems, right? We could, like in your deep learning code, right, could be fixed by hybridizing, right? But we only found about 55% of those. But the remaining 45% were due actually to existing usages of TF function, which is interesting. About 25% of the cases, performance fixes involve actually changing the arguments to TF function, as we saw in some of the tensor spec example, for example. So they may have to add an input shape or change the input shape dimensions or wildcards, etc. About 20% of performance problems involve actually incorrect tensor shape specification. So this is actually like one of the interesting things I think for future research is that like one big thing in like stack analysis of TensorFlow programs or deep learning programs is input shape violations, right? Compatibilities. So I think what it might be interesting future work is actually looking at how like the violations occur in hybridization specifically. So those are kind of more, the other works are kind of like more general. Especially when you're passing like tensors through APIs, definite shape problems. I think there was like a paper like 2020 maybe that discussed that. So yeah, so it'd be interesting to see like how that would work in the hybridization case, since they're actually being used there as a tensor specification. I think I'm running out of time. I'll go through this kind of quickly. Yes, about 20% API misuse was like I think our second largest problem category. So that's not using it in respect, how it's supposed to be used in, as in the documentation states it to be. So about 40% of API misuse was caused by developers not understanding how to use hybridization correctly. We call it like API confusion. And to fix API misuse, TF function was actually removed about 30% of the cases, which was interesting. They just leave up instead of fixing it. In about 50% of these cases, developers actually abandoned hybridization due to API confusion, of which 62.5% resulted in runtime errors. So remember, you're dealing with a dynamic language here, so all these things are going to be at runtime, which could be problematic, especially for industrial applications. Execution mode incompatibility, where you have code that's not amenable to both modes, right? So if you run it in deferred or eagerly, it doesn't give you the same result as we saw in some of the examples. About 20% was the third largest problems, right? So basically, it's not as easy as like switching on and off the decorator, right? So the idea is like you decorate the function, you let the runtime handle the conversion, and you have a nice day, right? But that actually wasn't the case in about 20% of the findings. About 80% of the compatibility problems right to runtime errors, right? Crashes, basically, or unexpected results. So those don't surface until you actually run the program. Another interesting category was bugs with Tensorflow. So this is actually like a problem with the framework itself. Because remember, we were looking at GitHub issues, and a lot of times developers like to complain to Tensorflow about the problems you're having, right? And sometimes that's the fault of Tensorflow. So so these are cases where a workaround was offered, or maybe the developers waited for a new framework version. That was about 8% of the discovered problems. About 9% of these actually involve deadlocks caused by the framework. So that's, especially for industrial applications, not so good. All right, so I just have like some, what we did next, like after the quantitative analysis, we did a qualitative analysis. We looked at like, certain examples, like kind of like we saw in the beginning of the talk, but these are actually from like real code. Those were like just toy examples from documentation. And then we also like put a lot of quotes from developers about why they're doing things. So, so for example, here, I guess they had a problem with performance of this code, so they added TF function. Remember, this is eager imperative EL code, so you're not reaping the benefits you would from a deferred execution style. And so yeah, so one of the recommendations is the favorite TF function on Python functions containing imperative, otherwise you will execute code. Oops. So that. So performance is sort of like our baseline example. This one is with adding the TensorFlow tensor specs. So you can see here from line 1 that there actually was no argument to begin with. So here they're adding a bunch of tensor spec parameters to the input signature. So we saw that quite a bit, which I think, again, is interesting for future work on how to verify that's actually correct. So yeah, so arguments to tensor TF function, particularly involving input tensor shapes, are also pretty influential with respect to performance. So there's two different categories. We looked at like our sunburst diagram that we had before. There's like over specifying your input signature and under specifying your input signature. So under specifying was actually one of the most used problems that we found. So, or most prevalent problems. Actually, they didn't give enough information. And on lines 2 to 6 here, you can see that the performance regression actually was fixed by adding this input signature to a weighted distribution TF function. And this is the quote from the developer: to make sure it does not recreate the graph or retrace the graph, right, which will slow down training significantly. And we found a lot of times, like in the ML pipeline, that they were applying TF function actually to the training portion of that pipeline. Yeah, there's also with the D types that has to be correct as well. So yeah, so otherwise, right, a separate concrete function, right, is what I'm going to say here. 1 second. So yeah, so the sequence of tensor specs, right, specifies the intended TensorFlow shapes and data types that will be supplied, right? So you're basically telling the runtime, like, hey, this is what I'm expecting this function to receive. This is the update weights function. And if you don't do that, you get basically, in the old version of this code, you get a separate concrete function, right, for every instantiation of the graph. For each what's called inferred input signature, depending on the context, may be actually incorrect, which result in retracing. So our best practice here is that if possible, supply an input signature argument to TF function. So if you have any idea of what kind of the shape of the tensor that you're expecting for that function, do apply an input signature. And this is really akin to providing type annotations for dynamic languages, is what we thought of. So it's just with type inferencing. So I think I'm running a little bit out of time. There's some more best practices that you can find in the paper. We have it up on archive, the preprint. Yeah, so if there's incompatibility, you can check the documentation to see if additional steps are required to make that code more readable. Hopefully, there could be some future automated support for such a thing. There could be some framework limitations that could impede performance. So there could be potential workarounds, right? Bugs with TensorFlow, unresolved perhaps. So maybe check even GitHub issues. Another thing we found was that so you can't debug easily when you have a hybridized piece of deep learning code. So what developers would do is they would remove the annotation, right? Do the debugging, right, in eager mode, and they're supposed to add it back, but they forgot. So they basically have performance. They later have performance regressions, only to learn that it was because they were debugging and they forgot to re-add TF function. So one suggestion we have is actually to turn it off globally using this flag here. If you're going to temporarily disable it to facilitate the debugging.
Why do you need to disable the debugging?
Because it's not easy to get to like the individual variables because it's basically compiled into a graph. And you're working with like dynamic language, so you may have dynamic features like interacting with that code. So there's certain cases where it gets a little bit cumbersome. And it's actually like akin to earlier in the talk where I said like, oh, deferred execution is not easily debuggable. It's because of how the graphic computation is built ahead of time, and it's not executed until later on. Yeah, because you think about it, the debugger, right? You're stepping through your code.
Yeah.
If you step over a statement that's being executed later, it doesn't really help you, right? Like you gotta wait. It's just like cumbersome. You know, another interesting thing about this work, this area is that, you know, a lot of times this code is not made by like expert programmers or developers. They're usually data scientists with like, you know, life science backgrounds or like some other, you know, non-engineering background. So that's another interesting thing. Like they're not really like classically trained software engineers. So this is one of our recommendations. Like, hey, you know, just replace this flag. And do your debugging, turn it back on. And
Yeah, I can see this debugging thing being a big issue because you're debugging it by running it in an execution model that's completely different from the actual execution model.
Right.
Yeah.
But
So it's like
convenience.
debugging a concurrent program by running it sequentially.
That is a problem, isn't it? Yeah, as I was saying that, I was thinking of the same thing. But it's much more convenient.
Yeah.
If you have a sequential bug, you've also got a concurrent bug.
That is true. You'll never find those concurrent bugs if you run it sequentially.
That's correct. Yeah, if you have a bug in graph evaluation, you're, I think, generally hosed in this scenario.
Right.
You get to go post an issue on Tensorflow and you get to say, you know, this isn't in our quarterly goals. We'll look at it in 6 months.
Sure. Yeah, another thing too is you can have code that runs great and eagerly, right? Because you have this thing off and then you turn it back on and it doesn't do what you expect. So yeah, so testing, yeah, the debugging is definitely an issue here. We have these two different modes, so. Yeah, so just in the paper, there's more stuff, bug pattern, more examples. We have encounters, recommendations, best practice. I showed a couple of best practices that preliminary best practices we come up with. Here's some discussion, you know, like future directions. Again, here's the URL if you like. It's also my website. You just Google the name of the paper as well. That's how it work. So in conclusion, we studied hybridization bugs and challenges in migrating imperative deep learning code to graph execution, right? Where you start with the otherwise eagerly executed deep learning program, and then let the runtime do the legwork for you to speed up your deep learning model in software. So we found, right, despite the purpose of hybridization, you actually must take pretty good care to avoid any performance degradation, which is again the opposite of its intention. We found that not all imperative deep learning code in a wild is amenable to graph execution, and that you should be cognizant of when your code is running in graph mode and when it's not, and how, you know, the two may communicate, right? So you may have one piece of code that's hybridized and another that's not, as I mentioned before. So for future work, we can look at some other sources of information. For example, we didn't look too much at Stack Overflow. Some of the quotes we used actually were from Stack Overflow problems, but in software engineering world, this is like a big data source for empirical studies. So we didn't focus on that because we really want to focus on the code. So that's why we picked Git commits, and we picked issues that contain code snippets. But also Stack Overflow has like code snippets as well. And some people do like program analysis on that, which could be interesting future work. Yeah, we'd like to actually automate some of this and maybe, you know, find violations of tensor specs input signatures. You know, maybe using SMT solvers, or maybe some kind of static approximation, or maybe a hybrid dynamic static analysis, some future directions there. And yeah, lastly, as I mentioned, it'd be cool to integrate our results into like these automated refactoring detection approaches, so that becomes like a category, you know, as it's mining these Python chain sets, Git commits and stuff. You know, that's one of the categories that come up. And those are used by a lot of like other researchers. Probably not so much practitioners, but a lot of like research, like software engineering or HCI researchers that develop tools. Like, for example, like one thing they use it for is to like derive Git commit messages. looking at the chain sets, and they use this refactoring tool, authentication tool, and say, oh, you refactored it. It's kind of an NLP thing too. So, but I could like feel some future research from like other groups maybe. NLP's not our strong point, but. And I think I said, yeah, thank you for your time, and I'll take any questions if you have any.
Okay, let's thank Raffi. All right, any questions?
I have a very high-level question. To what extent do you think that people developing TensorFlow realize that they are working on a language runtime, and that the problems they have are language runtime issues? And like many of the problems you discussed are the sorts of things that come up in, say, V8, right? What's the difference between slow path and fast path? How do you make sure it's going to run exactly the same code? These sound like sort of like classic JIT bugs on some level.
Right. So the person that made Autograph, I think is the languages person,
Okay.
like a languages runtime person, and Google hired him. So he's like behind all the Autograph stuff, and he has really detailed videos like of how like Autograph works in the background, and it's all like language centric stuff and like runtime stuff. I'm pretty sure he knows like that the answer to your question is yes. I don't know about like your kind of like rank and file, TensorFlow developer.
Yeah.
How much they know that's what they're working on. It's actually an interesting question. So
yeah, I mean, I see some of the sort of the bugs and gotchas here. I'm like, okay, I understand why you need to restrict recursion because you're going to try to really transfer it to a graph computation. But to me, it seems like bugs that are sort of like showstoppers for a JIT. Like, this is going to give you a different semantics. This is not going to correctly handle side effects. Like, you would turn it off. You would take the slow path. You would like say something about it. And I'm just like surprised that they're not doing that. Is it just too hard? Is it low value?
yeah, great question. Maybe it's the way they frame the problem, that they're not looking at it. Like, so one of the things that we found, like, and also what the researchers found, is like there's this kind of disconnect between the clients and the framework.
Right.
Developers, right? Like the framework developers are like, all right, I got to make this, I got to improve this, to this. But then the clients are calling the same function multiple times, and it's completely ruined it. So they're probably not thinking from a client perspective. I think it's like I would guess.
I mean, so you have a broad. I don't want to monopolize question time. I'm sorry. You have a broad suite of clients. Is it like are NVIDIA savvier? Like, are there like is it just like student homework where they're like doing like absolutely bonkers stuff?
We found this all over the place. Stuff.
So it's just amateur hour.
It's we actually found TensorFlow developers making mistakes with that function.
Yeah. So I mean, that's
it's just like nobody knows how to use it.
Yeah. That's pretty damning.
Yeah, you have to like respond to some issues and stuff. They can get back to us. But we think there are problems here.
They're quietly submit a patch.
There you go. Yeah, that's another. Yeah, that we should incorporate that. Like, so yeah, it really didn't matter. Expertise for kind of didn't matter. We really found it across the board.
Yeah, I mean that if anything is an argument against manual hybridization, right? If the experts can't get it right, who could possibly?
Or at least tools to help them do it correctly.
Yeah, something, yeah. But it seems like the runtime is also sort of culpable here in that it is willing to just silently fail or like silently break semantics. It's like, no, there should be a huge red warning that says something like, this code is not TF function hybridizable because you just side effected. What are you doing? And maybe it's just like the spurious, like, oh, I wanted a printf debug while hybridizing it now. And that's fine if I don't care about the, like, I wonder like how this disconnect happened. Like I'm confused how they got in this situation.
I think it's an analogous situation in a concurrent case, right?
Yeah.
So if you think about like a parallelizing compiler, like they didn't see that this code that's trying to parallelize is going to be completely wrong. Like, what
yeah, and it won't do it. Yeah, totally.
But I was thinking about that, but I guess the difference is that a parallelizing compiler everything is done within that compiler, but this is through this annotation mechanism. It's like this separate, it's not intimately part of the Python compiler. So it's hard you can't integrate these program analysis stuff with the information, or maybe
you don't
can.
have the information on how the client is using the function.
Right, I mean, unless, like, because there's not, is there a hook? Maybe I'm misunderstanding how annotations work in Python, but is there a hook?
They're just a higher order function.
Yeah, it's just they're doing code rewriting, so they're presumably rewriting it to implement appropriate tracing at appropriate points. But this is what makes me so confused. Like, when you see a call to a known side effecting function, like what a parallelized compiler does is has annotations for every primitive that says, does this cause side effects, and if so, of what kind?
Right.
And it seems like they've just sort of said YOLO, which to me is not a thing that a compiler writer gets to say, because your YOLO covers many people. This is more of a solo.
I mean, maybe like they're also thinking like about their customer base, right? It's not like software engineers that know like about UGC and stuff inside the hybrid.
Yeah.
You know, like, okay, saying this is modified, you know, this is immutable, is maybe, you know, really catering to like a data science grad. That could be another thing you're thinking.
Yeah. I guess it's definitely a perspective question, because to me, the idea of catering to someone by letting them do things that are bad and wrong silently is killing with kindness.
Right. That's a good way to put it. I think from my perspective as like I don't know, automated refactoring researchers, that I wouldn't want like the runtime or even compiler like doing things I don't know about. I mean, like kind of circumventing my problems. Like I want to change that in the code.
Yeah.
And it's because I write algorithms that do source semantics for human transformations, right? Like I want that committed in the code so I know as a developer I can reason about what that code is doing.
Right.
Because that could be another thing too.
Yeah, I still don't know why you wouldn't warn though, because they could.
It does in some cases, like so the retrace warning, right, was one case where they are warning.
Right. So I mean, maybe it just tells you what their priorities are. They warn you when performance gets bad, but they don't warn you when your output will be nonsense. Which is machine learning. It's approximate commuting. Like, who cares?
Maybe you think that's what you wanted.
Yeah.
Right,
I wanted nonsense.
There's no formal spec, so.
Yeah. All right. Okay. I'm not the other.
Yeah, it does seem like there could be some improved like validation. I don't really have to follow up to that, but like they could just like have like it doesn't, if it's validation, it doesn't have to be 100% accurate. It could just be like, hey, maybe there's something fishy going on here, especially since like you're looking at these different kind of bugs, finding at least a few common patterns. Like maybe, oh, your shape is underspecified here. Did you intentionally leave that out?
Yeah, it kind of reminds me of code spell detection.
Yeah, exactly.
That sort of thing, yeah. Like, we think something's wrong here, we're not quite sure, but maybe you should know about it, you know. Yeah, then you kind of get into static analysis, like, you know, false positive alerts and stuff.
I mean, worst case analysis, or worst case situation, you just put a no warn, whatever.
But the other thing too is like, you don't get this until runtime, right? Like, you would want to know this ahead of time. Like, and your arguments and stuff like that, so.
I mean, just run the code once to get one.
Well, it depends, yeah. At this time you do. But maybe, you know, it only happens in certain cases, right? Depending on your coverage, right? Your test coverage there.
Is it deterministic execution or non-deterministic?
Considering that explainability is a big research topic in deep learning, maybe like from our perspective, we're not quite sure how the results come. But I'm pretty sure it's deterministic in that, you know, if you have the same output and configuration parameters, you should get the same output there. But other than that, I think like it's sort of a mystery how deep learning works, I think, in general. Like how the neurons actually.
But the compilation is deterministic.
Yeah.
Right? Like if I give you the same program, I'm gonna get the same graph out every time.
And the execution of that graph at runtime is also deterministic. That was the question I had.
That's not true, because you're gonna get different seeds in every run.
Oh.
Right? Like your initial configuration is gonna be your graph is all zeros. Like they're gonna set it up differently from that, I think. And this is what like what the lottery ticket hypothesis is all about. It's about getting good random starting positions that let you learn the good models in the first place. I think I'm very outsider here.
Any other questions?
I guess to kind of follow up on the point, like the shape of your graph should still largely be deterministic though, and I feel like that accounts for a lot of the errors that we're seeing. So I think some kinds of analysis would probably still help here.
Yeah, I think it's definitely a prime area for analysis for the developer tool. It's a little bit of a niche area, but it's pervasively used in this area, I hope.
Cool. All right, let's thank Raffi again.
I guess we'll